So let's today look. Let me see. So the Fourier analysis of the linear potential theory problem means this. We have Laplace's equation in a flat bottom region. We reduce the free surface conditions to only this condition at the undisturbed level, and we have the Neumann condition at the bottom, right? So we have a problem like this. We'll put the origin here. We're doing the dimensional case. So notice that we're doing the dimensional case. Flat bottom. Our domain is fixed. It's not a free. The linear problem is not a free boundary problem anymore, so it makes our life easy. Okay, and say at the end, say what I mean by after the end, after we solve the problem, solve for the potential, we have that the wave elevation is equal to this. So now at eta, the wave elevation becomes what I can call a passive variable. Passive in the sense that it sits on the chair and it waits for you to solve it for the potential. After you're done, you just do this, right? In the free boundary problem, no. Actually, we don't know where the boundary is. Here, right, as a bonus from the linearization, we get the free surface condition can be applied at the undisturbed level, right? And here we have the dimensional problem. You can do the same thing I'm doing here for the dimensionless problem. Okay, so now what I want to do is the Fourier analysis, or in other words, the dispersion analysis for this problem. So I indicated that for the linear hyperbolic problem, okay, and that's, for example, a recommended exercise to do all the details. Now here I'm going to do, right, the part which is a little more complicated for this problem. So the Fourier representation for this problem, I only worry about phi, okay? So I'm going to say, okay, phi, the potential, has this Fourier representation, namely as a Fourier transform. If we were in a bounded domain or periodic, whatever, you could do it with Fourier series. Doesn't matter. So Fourier transform. And look now a difference. It's a little different, and it's more complicated than what we saw last time. Okay? So let me highlight this. This is important. So what am I telling what are we telling our audience right, of what we're thinking. So what I'm saying here is that I'm on the whole line. So on the whole line, I have all wave numbers. Okay? So just as a little indication to you, remember, if I have it on the fixed domain, say from 0 to L, I cannot have all Fourier numbers, right? Because I need Fourier numbers that say, that fit in my domain, right? As a periodic thing. So here we're on the whole line. So let me erase this. And so we have all the Fourier numbers from minus infinity to infinity. So we have at first this improper integral. Let's assume it makes sense. It's a good, all is fine. And now look, we have a difference here. So now I have a Fourier. This is our typical Fourier mode. Right and left going Fourier mode. Okay? This is what I would call the amplitude of my Fourier mode. So this Fourier mode here is at the free surface. So it's basically, let me continue this picture like this. Okay, if this were a Fourier mode, the real part, like a cosine or a sine, doesn't matter, right? Just the schematic. This is a guy living on the free surface, going to the right. This is a guy just like that, but then we'll move to the left. Okay? This is the temporal frequency. This is the spatial frequency. And the dispersion relation is basically an equation that relates both of them. And that for a linear constant coefficient problem, we can sort of transform a differential equation into an algebraic equation. Okay? So you'll be seeing this in many ways in actually easier problems in all detail today, but as an exercise, a good exercise to think about these slightly more complicated situations. So look at this. So this is the Fourier amplitude of this, that means of this Fourier mode. The same thing here. But now, if you look at the case I did last time, the Fourier amplitude did not depend on y. The Fourier amplitude depends only on k, only on the spatial frequency of the mode, right? So last class, I had say, for example, for eta, I'm not going to write, or else I'm going to spend too much time. So I had like a or b or eta hat here, which is the amplitude of this mode. Now, what I can say in words is that this amplitude of this mode depends on the depth, right? It depends on the depth, okay? And another way of saying this, so this is like a more physical way of saying this, right? This is the amplitude, depth, dependent amplitude of this Fourier mode. But actually what I'm going to try to do, which amounts to the same, is that I want to make now this guy and this guy, I need these to be harmonic functions. So I'm asking, are these harmonic functions? Because these now need to satisfy Laplace's equation. The problem is linear. If the problem is linear, I can do superposition. I can sum all possible solutions. The integral is basically saying that. I'm summing, I'm superimposing. This means, in words, I am superimposing all Fourier modes and their respective, this is a nice way of saying it mathematically, and their respective harmonic extension through the domain. Because this guy is on the free surface, and so it's like the Dirichlet data of this guy, and now I need to do the harmonic extension of it down into the domain, plus I have to make it satisfy a Neumann condition at the bottom. So that's what we're going to do. So the first step is make this guy, make this Fourier amplitude, which is a sinusoidal, cosine or sine oscillation on the free surface, it depends only on x and t, make this a harmonic function, meaning satisfy Laplace's equation, right? And then satisfy Neumann at the bottom, and then after we're done with that, then we make it satisfy the evolution equation. And then we're going to get, when we make it satisfy this, we're going to get the dispersion relation. That is, the temporal versus the spatial frequency, how do they relate? And as you will see, this simple problem is dispersive. Then you'll see exactly the definition of dispersion. I already indicated this last time. And you see it's going to be a complicated dispersion relation. This is the plan of our calculation we're going to do next. Okay? So I can say this in many words, okay? Just repeating again. I can think of this as the depth-dependent amplitude of the Fourier mode of spatial frequency k, which is the wave number. Or I can think of this as separation of variables, x and y, so that I can do the harmonic extension over my domain. Okay, so now let's compute things. So let's substitute this here in Laplace's equation. Okay, so if this bilinear superposition, I can just do a generic mode, right? I just got a generic mode, so we get this. So when we substitute this, we get this. I'm going to get an ODE. Okay, and I get the Neumann condition, also this. Okay? So this, if I substitute this in here, the XX gives me this. The YY stays here. It's an ODE because this depends only on one variable. So it's a little bit like a Sturm-Liouville problem. It's very simple, right, in that direction, satisfying this condition at the bottom. Okay? So it's very simple to see that we have two linear independent solutions to this guy, which is cosh Okay, so from this guy, we get two linearly independent solutions. You might think, how to get the cosh in the sinh? Well, actually, right, so the sinh should be like this. In Portuguese, it's sendo with an E. And look, this is a very simple equation, right? This is like exponential plus or minus ky, okay? But if you have an exponential, so the only thing I'm doing here is that if you have the exponential e to the plus or minus ky, you recombine them into a cosh and a sinh, a hyperbolic sine and a hyperbolic cosine, right? The hyperbolic sine is just a half of one plus the other, blah, blah, blah. And why? Because these are also two linearly independent solutions of this equation. And these are easier for me to then verify the Neumann condition at the bottom. Which one satisfies the Neumann condition at the bottom? This one. Because the derivative of the cosine is the sine, and at the bottom, y equals to minus h naught, it's 0. So I satisfy this. And this one then, I forget. I don't, this homogeneous solution is not needed in the solution. Okay? That's all there is. So therefore, we have that is equal to, I can put this notation here. Look. Okay? Because now cosh times e to the I blah, blah, blah is a harmonic function. Okay? Well, now we still need to satisfy what we call the linear, quote unquote, free surface condition, because it's not really a free surface, but anyway, we call it the free surface condition. Phi tt plus g, which is a constant, the gravity constant equal to 0. And this will give us the following. Oops, this is wrong. This y is equal to 0. Okay, then this simplifies with this, and here's the dispersion relation. Okay, and actually if you want the phase speed, which is okay, you see that this is going to be, say, divided by k squared, there's going to be c, is going to be square root okay, so let me actually put this to indicate. So it's actually very dispersive in the sense that the Fourier modes, their speed varies with their wavelength, meaning with their wave number, in a very dramatic way. Okay? So if we do, for example, the limit, I mentioned this last time very quickly, the limit k equals to 0, which is the shallow water limit, okay, we get that this is square root of g, excuse me, h0. Because as k goes to 0, this is just k h naught. K cancels with k, boom, right? And so the limit, the shallow water limit, let me write it. The shallow water limit is, let me highlight this, non-dispersive. Why is non-dispersive? Because it does not depend on k. And actually, as I showed you, right, the shallow water limit, if you do this with the dimensionless variables and so on, you see it's actually the equation we saw before, the very simple wave equation, which is hyperbolic. So the shallow water limit is actually hyperbolic, right? And then there's the short wave limit, or the deep water limit, short wave or deep water limit, and this is going to be the square root of g over k. Okay? That's very simple because hyperbolic tangent goes to what? To 1, right? So that's when you're very deep water. Okay, so if you have little, in the swimming pool, if you have little ripples, little small waves on top, they're in the deep water regime, right? Which is the same thing, the deep water regime is the same thing as beta going to infinity, right? Because beta is equal to h0 over lambda squared. So either short waves, which is this going to 0, or deep water, this going to infinity. Okay? So you can and you should maybe as an exercise just to see, redo this calculation for the dimensionless problem, and you will see that the dimensionless dispersion relation is like this. This is the dimensionless dispersion relation when beta goes to 0 and when beta goes to infinity, blah, 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 okay? So what else I want to say? Okay, yes, I have to mention one more thing. Maybe it's better to come over here. Now look, let me write this over here. Let me repeat here. Omega is equal to the square root of g over k hyperbolic tangent of k h0. Now look how the linear problem, this problem that looks quite simple, how the linear problem is easy to solve formally, but it's very hard, namely impossible, to get a closed expression for the solution. Why? Look, substitute in here and in here. Substitute this expression and try to integrate this. Complicated, right? I mean, no hope, right? An exponential to the square root of a hyperbolic, I mean, right? You can do asymptotics with it, but you cannot find the solution in closed form, right? So you can find it only as an integral representation. And there, I'll mention this, there's some regimes in which you do some asymptotic approximations, blah, blah, and you can more or less see in an approximate way how the solution looks like, right? And as I mentioned to you in this course, one thing we want to do is find methods, approximate methods, to have an idea of how the solution looks like, right? And many times doing this fully rigorous is very difficult, particularly when you have variable bottoms and so on, right? On the other hand, functional analysis of these problems, in particular of dispersive problems, is very hard because of the same reason. But functional analysis usually wants to do it and is capable of doing, and not all the time, giving you a theorem, a result, rigorous result of the smoothness of the solution, so on, but not always you get to see how the solution looks like, right? So this is the interplay and these important aspects of mathematics. Okay, so as you see, we plug this in here, it gets very complicated. So the best we can do is, this is an exact solution as a Fourier representation, but how does the solution look like to do, can I sketch this? It's very complicated. Okay, so let's look then at our Boost-Nesk systems, which are simpler and are good approximations. And these are difficult problems in functional analysis, in particular for the nonlinear case, to show how close the solution of the reduced problem, say a Boost-Nesk system, is to the full problem, which is potential theory. And as I mentioned, even proving the existence and well-posedness of the 3D nonlinear potential theory problem is something quite recent, you know, the rigorous proofs and all that. Okay, so let's then go to a Boussinesq system. So let's go back to, let me say it like this, to one of our Boussinesq systems. Namely this one. Okay, so you go back some pages of our notes, right? And you differentiate this with respect to x. So this is the Boussinesq system, which was on page, I think, 76 of the notes. Okay, this is our nonlinear, weakly dispersive Boussinesq system where this u tilde is the velocity at the bottom. Okay, so then here's the first question you see. I'll give you references in a little while, including very good people in functional analysis analyzing these systems. So the first question is, you get this from potential theory. Okay? And then you say, okay, doing the functional analysis of this problem is very hard. Okay? Comparing it to the full system is not trivial and so on. So there's a nice paper, I'll give you a reference of functional analysis. But then the first step is, okay, I don't understand this guy, right? So let me first then try to understand its linear version, right? So the linear version, which is basically put like this, alpha equal to 0, is this system. Okay, so all we made was alpha equal to 0. And now let's do the dispersion analysis of the linear system. Okay? Right, the dispersion analysis usually is for constant coefficient linear systems because it's a Fourier analysis where you do the superposition of modes. And then you get this, look. As we did before, well, let me do this. Let me show you to this so I don't have to rewrite things. You can just go back and look at last class. Last class, I did the Fourier analysis for this guy. And actually, I'm suggesting to you exercises to do the full detail of this guy, right? And the Fourier analysis, I mean, to get the coefficients and so on and so on. Now I've added the dispersive terms. Let's see what that does. Okay, so what I'm going to do is I'm going to substitute modes. So using, let me put it, dispersion analysis, like use e to the I kx minus omega t modes. Well, I don't even have to put this. Let me just put it like this. To get the following condition. is equal to 0. So let me just remind you, basically what we're solving is we're solving a system with maybe, I think it's u hat, eta hat, which equals 0. So this guy gives us this. Okay, do you recall what I'm doing? Right, I'm going a little fast. I mean, not so fast. I mean, if you're up with the material, you should know what I'm doing, right, from last class. So let me drink some water that you think, and I'll explain, right? And you'll check on your own afterwards. If you don't remember, which is not dramatic. So what I'm doing is, this is my linear system of PDEs, and I want to do a Fourier analysis. So I put what we call also a propagating mode. Right? Do you agree? This is a propagating mode, right? So I say, okay, I'm going to do a Fourier analysis. Since it's a linear problem, and since I can superimpose all the modes, take a generic mode. The generic mode will tell me a lot, will tell me how things work. Plug this into here. Now remember that I have to plug one of these modes. It's going to be u hat times this, and the other mode is going to be eta hat times this, which means the amplitude of the speed and the amplitude of the wave elevation. When I plug this guy into here, as soon as you do this a few times, you become like an expert, because you see, time derivatives will become minus e omega, minus I omega. I'm speaking Portuguese. Minus I omega. Here are the minus I omegas. Derivatives in x becomes powers of ik. Ik. And here are the powers. Look, third derivative, 1 in time, 2 in space. 1 in time, 2 in space. Right? And then, since this PDE becomes an algebraic system of equations equal to 0, homogeneous algebraic system of equations, I do not want a trivial solution, which says the amplitude is 0, the amplitude is 0, because then there's nothing happening. There's no dynamics. Right? So the only way that I can get something non-trivial is imposing that the determinant of the matrix is 0. Right? And from this determinant, we get, okay, the dispersion relation. Okay, so we get the dispersion relation. Okay, and this dispersion relation is in the form of what we call a Padé approximation. You know what a Padé approximation is? It's basically a rational approximation of something. So that is a polynomial divided by another polynomial. Here the polynomial is a polynomial in K. So this is, as I will show you this, we will see that this is a Padé approximation of the full dispersion relation. Okay? What is the full dispersion relation? Is this one. Now the dimensionless one. Okay? Of the full dispersion relation. Okay, so let's check a few things here. Let's check a few things. I even forgot to put this in the notes, but look at this. Now we have some, we can do some consistency checks. Okay, which one will be the Padé approximation. So the first consistency check is, what does this give us? Look, this system here is a system for weakly nonlinear, weakly dispersive waves. Okay, this system here is a linear system for weakly dispersive waves. It's already linear, weakly dispersive. What does weakly dispersive means? Weakly dispersive means long waves. Okay, long waves. Now, so if we go into the shallow water regime, the long wave regime is allowing beta to go to 0. If beta goes to 0, we get omega squared is equal to k squared. That's exactly what we saw last time, right, for this system, of course, which is the shallow water limit. Okay, now the other important thing is this. Let me see, I can put it in the two, yeah, I can put it here in this same blackboard. So this expression here, okay, check this. This expression here, I can write that omega squared is approximately k squared minus beta over 3 k4 plus order beta squared. Okay? More details are given in the notes, but how did I get that? That's very simple. This guy here, I can expand it, right? I can expand this guy, and I get this. In particular, if this is small, you can even use the geometric series, the first terms of the geometric series. But if you expand, you get this. Now, if I expand this, so what do you see? This is a good consistency check in our asymptotic regime. Do you see what I'm saying? Without me pointing? I will point to, right? I'm just doing a little mental exercise. I've just done a consistency check that during my reduced modeling, my truncations, blah, 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 that we did last time, I did not do things too wrong. At least to start with, things are okay. Why? Because the dispersion relation that I get here, to first approximation, that means for small beta, it is close to the full dispersion relation. How did I check that? Well, this is a Padé approximation, which is a good approximation in many ways. So if you see it appears in numerical analysis and so on, it basically, instead of approximating something by a polynomial, that's what Padé approximation is. Instead of approximating by a polynomial, you approximate it by a rational function, which is a polynomial divided by a polynomial. Here it is, a polynomial divided by a polynomial in K. Okay? But then, so I can compare both dispersion relations. Look, let me expand this guy so I can take a look at the leading terms of this expression. Here are the leading terms of this expression. If beta is small, basically I have this fourth order polynomial. Okay? Now expand the hyperbolic tangent, and if you also group terms, you see that to first order, it is also fourth order in K, and these two leading order terms of the polynomial approximation are exactly the same as these two. Which means in the physical applied interpretation, which is the important one here, is that the phase speed should be close, which means if I divide this by k to get the phase speed, right, waves from this guy will propagate with approximately the same speed as waves from this guy, dimensionless version, because this one is dimensional. Okay? So this is what I've done is exactly to show that to leading order, which means for small beta, which means for shallow waters or long waves, the wave speed will be similar for this system or for the full system. Okay? And when we use this notation here, what I'm saying is that this guy here, which is a constant times beta squared, does not need to be the same, and probably is not the same, as this guy times beta squared. But it's of the same order. And if beta is small, it's a little, right, something that shouldn't matter. So you understand the philosophy of the calculation, right? So this is, this is basically what we need to do. But then, remember that I said before that we have, remember that I mentioned today, I said we have infinitely many Boost-esque systems that we can deduce from potential theory, basically by playing that game of changing one derivative for the other, which is things that I also recommend in the exercises we see on the board and so on. Okay, you can exchange a time derivative for a spatial derivative up to a certain order and so on. So we have this system, and then we played with it to change this u to it, whatever, to get something that looked like the standard Boost-esque system. Okay? So let's look at the following system. Let's look at another Boost-esque like system. Say this one, just as an exercise. Let's look at this one to see, so that we can see things that might not go so well. That's the idea. No, I wrote this wrong, sorry. And this is kind of interesting. It has, so let me indicate why I'm looking at this one. It has a KdV-like term. Okay? So what is the dispersion? See, it's a little different. It's different from this one. Okay? It kind of lost this guy here. It's in the same asymptotic regime that we did. So we could get this system. Some of you could have deduced this one from the potential theory. I, for some other reason, I wanted to look a little bit like the KdV. I deduced this one. They're all fair because they're in the same regime with the same rules of playing with terms, but the dispersion relation will be different. So let's check that. So here, the dispersion relation, right, will be then, we'll get this, the determinant okay, so we see here, right, the first equation, derivative in time, derivative in space, derivative in time, okay, and this derivative in space is this. This gives us the dispersion relation which is this. Right. And now let me ask you a question. Okay, so if you compare this system, so let me call this maybe square 2, And this dispersion relation here, square 1. Okay, so here's a simple question, but might not be that simple because it's the first time I'm asking you. So that's why think of it as fun. It's going to be, what is André asking? Look at this. So if you have this system, if I gave to you this system, and also this system, which, as I said, are legitimate asymptotic systems, look, the dispersion relation of this guy to leading order matches this one, okay? Okay, now I ask you, because this course is about applied math and choosing things and choosing the model, I say, which model do you want to work with? In particular, why? Looks more simple. Let me repeat things in English also that the microphone captures it, right? So you might prefer to work with that one because it looks more simple. Yeah, that's maybe why it looks like KDV a little bit, right? How about you? Do you have any choices? That other one which is more simple, right? Well, yes, that's a good way of, saying you want to buy that one. Let me tell you, no, it's worse. This one's better. But I agree with you too. I agree. I mean, at first it looks like, yeah, I want to work with that one. It looks more simple. Let me show you now why I don't want to work with that guy. I want to work with this guy. So that's fun, right? And it's simple. Let's do this. Look. Even though, here's the thing of the mathematics. Even though physically we are working with long waves, right? But when I do the mathematics, I mean, if I do, say, if I put here for this problem, or the other one, a wave, that's like this, as my initial condition, which is a Gaussian, right? Just a Gaussian in the sense of a smooth hump of water. The Fourier transform of a Gaussian is also a Gaussian, right? That's why Gaussians are good to use as test waves, because it looks pretty much the same in Fourier space in physical space, and there's that thing that reminds us things of uncertainty principle, so on, which is if the Gaussian is wide in physical space, it's skinny in Fourier space, which means it only needs just a few modes. On the other hand, if the Gaussian is skinny in physical space, it is wide in Fourier space because it needs a lot of modes. Well, if a Gaussian is a Gaussian in Fourier space, that means it's using all the Fourier modes because of its Fourier representation, even though it's a long wave, right? I mean, those modes are exponentially small, but they're non-zero if you do the Fourier transform of your data, right? And here it is. It's represented, well, it's represented there. It's represented from plus or minus infinity. So let's look at these two dispersion relations in the long wave regime, not in the long wave regime because the model is for long waves. Let's look, I said it wrong. Let's look at the two dispersion relations in the high K regime because of the Fourier transform. So when K is large, look what happens here. We have a problem. Let's look at this. Let me induce to you where the problem comes from. Okay, this is the phase speed. Okay? So the phase speed, look what happens. When the K is large enough, this number will become negative. And if we take the square root, we're going to get, we might get complex valued frequencies at a certain point. So this might generate instabilities. On the other hand, this one to leading order looks like that, which is a great thing because it looks like the full one, And that one was okay too because it looks like this one. But this one, when k becomes large, right? You see, it does not become complex. So actually this one, if you do it for k large, the phase speed, it's saying us that the high frequency components of the solution, when k goes to infinity, the speed will go to 0, which doesn't matter. It means that those modes don't move very much. And those modes are non-physical. They're only due to a mathematical representation of the solution. But they're exponentially small. Okay? So you see that this model has different properties from this model for high Fourier modes. Or that is, modes from the tail of the Fourier series, which are there not for physical reasons, because this is a long wave model. They're there for mathematical reasons, that is, for the Fourier representation of these smooth functions. They're exponentially small, but they're there. And if you do numerics, those things might grow because they're there. So these are the things that we have to worry with. Okay? So let me mention now about, let's do the dispersion relation of the KdV, so I can mention about another equation. And take this out so that we can get more space. So the linear KdV, right? The KdV appears in many forms. Let me write it in this way. Some forms are better to integrate and so on, but it's not such a big deal at this stage. Okay? And if we do the Fourier analysis and the dispersion relation, we get this. Okay? Or in other words, we get also this. Okay? So here, even though the KdV in principle is a unidirectional model, for this case it's a unidirectional model for waves propagating this way, for high frequencies, spatial frequencies, the speed might become negative. But this will be for very small modes and so on. And you can check, right, that that the leading order for long waves, this model and this model have similar, because that's why you chose. It looks simpler, it looks like KdV. So for long modes, that is for small k, the phase speeds are similar, right? But this one, might become negative. So then there's some very interesting things that I'm going to mention. Some very interesting papers of people who actually in functional analysis. So there's a famous paper by Benjamin, Bona, and Mahoney, which therefore gave rise to an equation called the BBM equation, because of the names of them, right? So this is a paper, 1972, in the Philosophical Transactions of the Royal Society. Of London, Series A. And look what they did. It looks just like a very simple minor thing, but had many interesting, and there's many beautiful implications connected with all this, which is, let me compare here. We have the KdV. Let me write it in the way that would more or less, I think, appear in their paper. And here's the BBM. Okay, so what happened here? I mean, the first thing, excuse me, the first thing in their paper is very simple, but there are many deeper and important unfoldings of all this. The first thing is very simple. Look, if you get, when I mentioned to you playing about exchanging derivatives, we did this before, exchanging a spatial derivative by a time derivative. We can do this here. Look, to leading order here, I can change a time derivative for a spatial derivative up to order beta, and then I can change this guy from u to eta. We did this before when we did the trying to find the standard, the classical Boussinesq system. Okay? So here, what they did is something similar. Look, here, if I look at this guy here, I can change one spatial derivative for a time derivative because eta t is equal to eta x plus higher order terms which are not appearing here. And then if I substitute this here, I change the higher order terms, but I don't change anything. And here's the minus sign. Okay, do you see what I'm doing? This is as I did last time, to exchange derivatives. Okay, that's how we change one time derivative for a spatial derivative. So the first interesting and simple impact of this change of derivatives, a spatial one for a time one, right, is that I change the dispersion relation, right? And an interesting thing is that when we change when we have sometimes mixed terms, like spatial and temporal terms, that's how we get the Padé approximation. Because we're going to have to see here, I'm going to get a omega k term. I have to add this omega with this omega, and then I throw the k underneath. That's how I get the rational approximation. So do this. It's in the notes, right? Let me give you the result. It's in the notes. So from the BBM, we get that omega is equal to k. You can double check this easily. 1 plus k squared. Okay? Which is approximately, for k small, is approximately k 1 minus k squared. Right? Just think of this as a geometric series, right? Whereas the KdV, omega, this KdV is k minus k cubed. So you see, to leading order, it's the same thing. But this is a Padé approximation, right? A linear polynomial and a quadratic polynomial. And you see that here, when k goes to infinity, in the mathematical Fourier representation, this goes to 0, right? So, okay, so basically here, I can say that high frequencies which are non-physical but play a role mathematically speaking, right, are okay in this case. So therefore sometimes because of this effect, equations like the BBM or equations with cross derivatives, they are called regularized long wave models. Okay, because this acts a little bit as a regularization for high frequency representation. So make sure that you understand, right? One thing is the high frequency mathematical representation, even though the model is a long wave model, right? I think that's clear, right? So here's my long wave, but when I do the Fourier transform, it has exponentially small modes from the mathematical representation. Okay? So let's see. Let me go to the other board. Use more space. Need more space. So I'm going to mention a few facts about these models. So facts, okay. A. Both KDV and BBM have what we call secant squared solitary wave profiles, which are basically traveling nonlinear waves. Okay, so I have to maybe ask the camera to follow me here because so I can use, I don't have to write again. Look at this. These are interesting things. I'm going to point out some things to you. Look at this. This first part here, what does this remind you? Just give me one name. Well, look, this guy is just a translation, a linear term, so erase this. This is Berger's equation, right, with this linear advection, right? If I put myself into a moving frame, this guy disappears and I get this, it's basically Berger's equation. So this is the same as Berger's equation, right? Now look how cool, here's something that's very interesting, which I'm going to mention a little more today until maybe we end the class, we'll see. But look this. We saw that Berger's equation generates a shock, right? Now, when I add a dispersive term in the correct fashion, right? Usually we have a alpha here and a beta here, right? And actually, we tune them to be epsilon and so on, but sometimes this is okay even like this when they're order 1, if they're in the right terms, right scales. So here, look what happens. A dispersive term, as I mentioned to, a dispersive guy usually, for the linear equation usually makes high frequency terms like an oscillatory tail fall behind your solution. On the other hand, the nonlinear term makes your profile steepening until it breaks. Actually, now, when you put correctly both terms, there's now an arm wrestling, right? A fight between two terms, one that wants to make the wave break and the other one that wants to pull an oscillatory tail behind. And if things are balanced, if this fight is a tie, you get a traveling wave solution. And what is interesting is that for the KDV and the BBM, the shape is the same, is a secant squared. And the secant squared basically has a shape like this. It's a solitary wave, right? Just like the one that reminds the one that Scott Russell saw in the Edinburgh Channel, the very famous, right, first observation of a solitary wave. It's a traveling wave that doesn't change its form, okay? And the solitary wave has a shape like this, which is this secant squared shape, okay? It's a traveling wave. How do you find the traveling wave solution of these equations, right? I'm not going to give you the details in the class. It's in some books. Sometimes I give it as an exercise. What you usually do is you say, okay, I want eta to be a function of this type. I don't quite know what the speed is, but if there exists a traveling wave solution, it has to be of this form because it's a wave of translation, right? I might not even know what the speed is, and actually the speed for these waves depends on its amplitude, okay? But the way to calculate the traveling wave for this one or this one, right, is you basically ask for a solution of this form. You plug this into here or to there. It will become an ODE in F, and you start integrating and imposing conditions on this ODE, and eventually the solution might come up, right? Not always this works, sometimes it's more complicated, but the KdV, it comes up, the BBM, and it's a secant squared profile with some adjustments, okay? So, very good. So this is already an important fact of, even though the dispersion relation is different, both have similar solutions. Okay, the other fact that I have here, I already mentioned. So let me put here fact B, or I have the one in the notes. So the Scott-Russell one, let me put it here. Single hump wave observed in 1834 is, right, post-shaped as the secant squared. C. Now comes then more difficult things to check, but I'm passing it to you as information, right? We're not going to check this in the course. But the KdV is also called, and it was very important for this, mathematically speaking, right? Called an integrable system. Okay, and basically that has to do with the fact that it has infinitely many conserved quantities. So one paper as a reference for you, those interested is Miura, Gardner, and Krusko, 1968. So in the 60s, KdV, many things were discovered and shown the KdV. Okay, this is just one of the things. So integrable systems, right? It has this, which is something else. Well, let me write and then I'll mention. Solitary waves are called solitons, right? And maybe Krusko, I don't know if it was Krusko that was one of the first people who gave this name. So do you know, I mean, these days, it's getting more, unfortunately, it's getting more and more misused, the name solitons, right? So many people just see a single humped wave, like they say, oh, this is a soliton. But actually, the origin of the name has a very specific meaning. Not every solitary wave is a soliton. The secant squared solution of the KdV is a soliton. The secant squared solution of the BBM is not a soliton. Okay? So let me write here. Solitaries are called soliton. So solitary waves, for the KdV are solitons. BBM solitary waves are not solitons. Do you know why? I would suspect that not, but maybe you know why. Do you know why? Yes. So it was responded here, and the answer is right. There is a difference when they interact. Okay? So it's like this. If I put a big solitary wave, I put a smaller solitary wave, and they're going this direction. Okay? Remember that I told you if you do that integration as an ODE, blah, 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 the speed depends on the height of the wave. I mentioned that. I didn't show you, but I mentioned to you that. So this means this guy moves faster than this guy, and it will eventually collide and run over. Okay? The fact, so the answer is good. The fact that the system is an integrable system, the collision of these two guys, it can be head-on or one running over the other. The collision of these guys for the KdV is called elastic, in the sense that they interact. There's a little bit of a phase interaction, something interacts, and then the other one comes out, and it comes out. My drawing's horrible, sorry. It comes out as nothing had happened. So it's like an elastic collision, right? There's nothing done to the particles. There's just two balls colliding, right? So therefore, since it looks like two particles, like two densities of particles colliding, right? And particles usually have the name at the end, the on ending. I forget now if it was Krosko, but anyway, this term was coined. Solitary waves are then called solitons, which is they look as a particle colliding. Now, when you do this for the BBM, right? And sometimes you look at in the computer, sometimes you have to look very closely. They don't collide perfectly. You see a little bit of what's called a dispersive radiation, which means, say, here at the back of the wave, after the collision, there's some oscillations, which is basically called, this is for the BBM, called dispersive radiation. So therefore, the collision is not perfectly elastic. It's not elastic. Okay, and that's an interesting field. Would be, for an expert to give a course on this. It has to do with integrable systems, inverse scattering transforms, and many interesting things in nonlinear dynamics. And we have actually books here at IMPA, and there's many very good books by important names, including there's a recent book by Ablovitz and others. I mean, this book only by Ablovitz. So the BBM solitary wave is not a soliton. Even though, unfortunately, you see in talks and so on, people see a solitary wave, calls it a soliton. And now you see the difference. You have to study more to say it's a soliton. It has to collide in an elastic way. Usually that's connected, related to the system being an integrable system. So it's not easy to prove, right? It has infinitely many conserved quantities and so on. So, yeah, these are things I wanted to, let's see, I think I have more comments here on the next page. That's right, here it is. So the BBM is nothing. And the BBM, so let me put it here. I think it has been proved that BBM has 3 conservation laws associated to it. That means conserved quantities, right? 3 conservation laws. So here's the comments is exactly this. It has oscillations can be found and so on. And I think I did not forget any comments. No. So let me write now, over here, right, the dispersion relation for the standard Boussinesq form. Standard dimensionless Boussinesq equation and remember that this U now is depth averaged. Okay? And then if we do alpha equal to 0, we get the following dispersion relation. And this is a good Padé approximation dispersion relation, which you can check to leading order. It looks like the full dispersion relation. Okay, let me do, I think, my final comment and leave the rest for Wednesday. So there's a paper also in functional analysis, because it has connections with what I said. So another fact is there's this paper, which is a series of 2 papers with the same authors. Very well-known analysts, particularly Bona and Sot, which are more senior and have been to IMPA many times to interact with the people here of our analysis group. So the first paper is linear theory. So it's some functional analysis with meaning the linearized Boussinesq type systems, right? The second part has some nonlinear theory because not everything is possible. So they study what sometimes was called the Boussinesq ABCD system. You'll see why. So what is the ABCD system? It's this. So I'm using their notation. They use W instead of U, doesn't matter. So see, they call this ABCD system because of they put these parameters here. A, B, C, D, right? And you can make some of them equal to 0 or whatever, right? If you do them make be equal to 0, you get some of these cases here, like you can get this case, you can get this case, right? And basically, you see that these can become coupled KDV, BBM systems, right? As you wish. You can play with a certain parameter regime. And they provide, in particular in some of the nonlinear problems, let me write here. This is one of the important results. They provide ranges in A, B, C, D for the problem to be well posed, right? Existence of solutions, sometimes stability, I think issues, and so on. So this was a paper that, two papers that this group, as I said, Jerry Bona and Jean-Claude Saut have been here. These two seniors ones have been here at IMPA many times. And they do the functional analysis of this, and actually there's some results, nonlinear results, and as they mentioned, full analysis is not simple. But you see, what we did is we looked at the linear version, which is a little bit what they do here, of some of these systems. Okay? So this is like from the functional analysis point of view. And I will stop here and come back to still issues on this on Wednesday.